Rightio, let's start looking at the meat of these nucleophilic substitution reactions and start defining our SN1 and SN2 and how they occur. So SN1, remembering S stands for substitution, N for nucleophilic, and then we have SN1 and SN2. These two mechanisms differ in the number of steps required for the reaction to reach completion. And the number 1 or 2 defines the number of species as being the chemicals involved to form the transition state. So both of these are going to have a state that they move to from the reactants into the products. One of them requires one species to form the transition state, the other requires 2. So for an SN2, 2 species are needed, and this is to form the transition state, which will be the rate determining step, i.e. the slowest step in the reaction pathway. Okay, whereas an SN1 will only require 1 species to produce the transition state in the rate determining step. Primary halogenoalkanes will always undergo SN2 reactions, tertiary halogenoalkanes will always undergo SN1, and secondary are going to undergo a mixture, and we won't refer to those in detail within the scope of this course. So the first thing we need to do is identify what we mean by a transition state. And a transition state is a reactive unstable species that is formed in one step and used up in the next. So it's never seen as one of the reactants or the products. It's an intermediate phase that we move through in the process. So generally they will need to be discovered in the mechanism, but there's no evidence of them in the reactants or the products after the reaction has occurred. So it's a step in the reaction mechanism that is often referred to as an activated complex. It's the thing that needs to occur for the reaction to complete, and the first step of the mechanism will usually be to form this activated complex. For an SN2 reaction mechanism, this occurs for primary halogenoalkanes, and it occurs in one step. Okay, there are 2 species involved in the formation of the intermediate, but the process is one step. The attack is happening as the group is leaving, so all this happens at once. So a primary halogenoalkane will only have small hydrogens attached to the central carbon, so we don't have a lot of steric hindrance around this electron deficient center. This means that small nucleophiles such as the hydroxides have room to attack in the opposite side to the halogen. So these electrons will move from the nucleophile into the electron deficient center, which will cause them to repel the electrons that are in the bond to the halogenoalkane. Because the halogenoalkane is electronegative, it can stabilize this negative charge, so it takes the 2 electrons from the bonding pair, and this process is occurring all at once. So we have the dative bond being formed in here, where 2 electrons are being donated from one species, and the breaking of this bond here until we get the final product. We draw this intermediate where we have both attached with dashed lines between the nucleophile, and you will notice it no longer has that lone pair or negative charge being shown on it, and dashed lines to the halogenoalkane to show that neither of these bonds are fully formed at this time. We also put the species in brackets, and the negative charge from the nucleophile is now up here being distributed across the whole molecule until the bond with the carbon is broken. This carbon-halogen bond is a heterolytic cleavage, so it releases the chloride anion and forms the alcohol product. So in these substitution reactions, as we've seen previously, we will get 2 products forming. The transition state, or the activated complex, is going to be at the height of our activation energy. This is the requirement for this reaction to be able to proceed, and is the highest energy species in this mechanism. So we will see that the nucleophile will come in, we form the dative bond, we have both species being attached in the intermediate, and then release of that to form the new product. So the characteristics of an SN2 reaction that we need to know is that it's a one-step reaction that involves two species in the formation of the intermediate, and that this unstable intermediate will quickly form the product. So the formation of the intermediate is the rate determining step. The transition state will have both the halide and the nucleophile attached, and this slow attack and fast displacement are characteristic of this reaction. Okay, this means that the rate of the reaction is dependent on both the nucleophile and the halogenoalkane in order for the right collision with the right orientation to occur. We refer to the SN2 reaction as a bimolecular reaction, i.e. two molecules required in the formation of the intermediate. The stereochemistry for SN2 reactions, and I want to clear this up so that there's no confusion after what we were talking about the other day. The nucleophile will always attack from the opposite side of the leaving group. This will invert our stereochemistry. So if we start with an S isomer, okay, because if we start with enantiomers, this one down here is not an enantiomer, but if we start with an enantiomer that is an S isomer, the product will be the R isomer. We get inversion of the stereocenter. The term stereospecific with these reactions, okay, means that we will always only get one isomer being formed. So we will always have inversion of the stereochemistry, but it can only ever produce one isomer. So if I start with S, I get R. If I start with R, I get S. We get that inversion around the stereocenter, and we will only ever get one isomer, so it's stereospecific. So that is when it occurs at a chiral carbon. When we don't have a chiral carbon, of course, we don't have enantiomers, so we don't need to worry about the stereochemistry. The SN2 mechanism will favor aprotic solvents. These are ones that are unable to form hydrogen bonds. So they should be polar, so they could be things like acetonitrile, ethane nitrile, things that contain organic compounds that contain a polar group, because our nucleophile also needs to be soluble in our solvent, but so does our halogenoalkane. Aprotic because groups that can form hydrogen bonds can also act as weak nucleophiles, so this will affect the rate at which our reaction occurs if the nucleophile that is desired for the reaction is competing with another nucleophile in the system. The SN1 reaction mechanism occurs for tertiary halogenoalkanes. These are ones where we have alkyl substituents on all bar one position, that last position being taken up by our halogen. This is a two-step process where the first process is slow, the formation of the reactive intermediate, and the second step is fast, remembering that the previous one was a one-step process, because we have the attack and the cleavage occurring at the same time. So tertiary halogenoalkanes will have bulky alkyl groups, these being R groups, that produce steric hindrance around that stereocenter. So it's harder for the nucleophile to have space to be able to attack the electron deficient center. Instead, what happens is that the halogenoalkane bond will cleave and we form ions. This means that we have the heterolytic fission of the bond, where both bond electrons from the bond move on to the halogen, forming the ionization. So we get the halogen anion, and then we get what we refer to as the intermediate, the carbocation intermediate. This makes a formal positive ion of the carbons. Carbons don't like to be charged, and so the next step is very fast. Once we have released this space to be open for attack, the nucleophile will attack, forming the alcohol, the tertiary alcohol. Okay, so the larger the steric hindrance around the central carbon, the more stable the carbocation is. Okay, so when we classify carbocations, we have primary carbocations, secondary carbocations, and tertiary carbocations. We are talking about these ones here in terms of producing our halogenoalkane from an SN2 SN2 reaction, okay? And the larger the alkyl groups, the more stability we have. So we see the bond cleaving first and then attack happening from the side. The thing with this is that the attack can happen from either side. So this means that we've got a non-stereospecific reaction. So it's a two-step reaction involving the formation of a carbocation. The carbocation is the rate-determining step, the slow step. It is stabilized, i.e. we have a positive inductive effect from the alkyl groups surrounding the carbocation. So the larger these alkyl groups, if they're ethyl, propyl, the more inductive effect that we see. This means that the carbocation is present long enough for the second step to occur. The rate of the reaction is dependent on the concentration of the halogenoalkane only, and therefore is referred to as a unimolecular reaction, the SN1 reaction. The mechanism, as we said before, we have the heterolytic cleavage of the Cl, then we will say that this produces the carbocation plus the chloride anion, then the carbocation is going to react with the nucleophile, with the electrons coming from the nucleophile into the electron deficient center to produce the final alcohol, remembering that the intermediate is not seen in the final product or the reactant. This means that we will have a two-humped energy profile for this type of reaction. This is the original heterolytic cleavage of the halogenoalkane to form the carbocation, and then the reaction of the carbocation with the sodium hydroxide to form the alcohol with an overall exothermic reaction profile. The stereochemistry in SN1 reactions, as we mentioned before, the carbocation ends up being trigonal planar once the leaving group has left, which means that the group can attack from above or below the plane. This means that we can get a range of optical isomers, either S or R, for a reactant that has a chiral center. So we say that this is a non-stereospecific reaction. The solvent considerations for an SN1 reaction are also a little bit different. SN1 reactions are stabilized by the carbocation because of the alkyl groups that surround it. The solvents that we choose for this now are protic. These protic solvents will stabilize the cation more, just like water does when it dissolves ionic compounds. Okay, so the negative side of the water molecule, the oxygen, will be able to form a hydration sphere around the carbocation, which protects its stability, allowing the nucleophile time to attack. Okay, so SN1 reactions will be favored by protic solvents, polar protic solvents, whereas SN2 are polar aprotic solvents. Okay, so this means that SN1 reactions are favored by reactions in water or alcohols or even carboxylic acids, whereas we want pure organic polar solvents for our SN2. In terms of secondary halogenoalkanes, these can show evidence of both mechanisms depending on the species involved, the solvent, and how hindered the carbons are around that halogen. We don't study these reactions because it's difficult to be precise about the reaction mechanism that is occurring, so you just need to know that a secondary halogenoalkane can show a mixture of both SN1 and SN2 reactions. That's it for our look at SN1, SN2. The next video will just clarify some of those rate considerations and how we talk about the rate determining step in the mechanisms of these reactions.